All right, welcome back to chapter 6, everybody. Today we're talking about enthalpy and calorimetry. Calorimetry is a pretty useful experimental procedure, so I would make sure you start to grasp this stuff. Enthalpy is going to be pretty big, especially for thermochemistry. So this is a nice section to make sure you're getting the hang of. So we're going to talk about two different kinds of systems, systems at constant volume and systems at constant pressure. Um, I'm going to say it's a common notation. A little bit of back history. My undergraduate work, I used the physical chemistry textbook by Donald McQuarrie, so my notation pretty much follows what he does. But here, when you see a subscript like here, that subscript volume, that's that's the quantity being held constant. So here you can start to see how these equations change based off what you're holding constant. So if you look here, you have delta U, or the internal energy of the system. Remember your first law of thermodynamics. But remember, this is also Q minus P delta V. And when volume is constant, there is no delta V. So that's zero. So when volume is constant, delta P delta V becomes zero. So you end up with delta U equals Q, but I put the sub V on it to show that volume is constant. And so you see at a constant volume, the energy of your system is just the heat energy. So here we have a new definition, H equals U plus PV. So uh, this is your definition for enthalpy. Of course, U is your energy of your system, and PV is the pressure of your system, V is the volume of your system. And so we want to make sure we get a couple of definitions down. That heat is the transfer of thermal energy between a system and its surroundings due to temperature difference. While enthalpy, it's a thermodynamic state function. So we're back to the idea of a state function, but it's the total heat content of the system. So they're slightly different. There are times when they equal each other, but as you solve exercises, you're going to want to make sure you're paying attention to units and whatnot. Um, so for example, you'll find at constant pressure, they equal each other, but they're not exactly the same thing. So let's start by looking at a system at constant pressure. Okay, so like we started with our first law of thermodynamics, heat plus work, or QP minus P delta V. So of course the subscript P means constant pressure. Then I rearrange this. QP delta U plus P delta V. And then let's break these apart to see what these become. So delta U, U final minus U initial, plus P times V final minus V initial. Let's see, then that's going to be U final minus U initial. And then we're going to factor the P across. So PV final minus PV initial. And so then this is going to be U final minus U initial plus PV final minus PV initial. And then I'm going to put my finals and initials in the same groupings. U final plus PV final, and then minus U initial plus PV initial. And so what you notice is with our definition of enthalpy, that's final enthalpy minus initial enthalpy, or in this case, at constant pressure, Q equals delta H. So this is a circumstance where enthalpy does equal, it equals the heat, but remember definitionally, they're not exactly the same thing. Now, there it is. Oh, where did I give myself room to do this? So now we're going to move on and do something you might not have seen before. We're actually going to look at our system in terms of differentials. So a differential is we've kind of talked about it. It's an infinitely small value. So if you think about like your cylinder growing, you have an initial volume, and then the cylinder is going to grow by these tiny little discs, just over and over just over and over and over again until you get a new volume, a final volume. Then you imagine each one of these discs is infinitely thin, and that's a volume element dV, so a differential of the volume. Now, essentially, what you're doing is your delta V is you're summing up all of your little dVs, except you can't do a sum for a differential. The sigma notation is for discrete mathematics. So what you end up doing is you take an integral, which is an infinite sum. So your integral, so you're essentially taking an infinite sum of all these little differentials till you get from volume one to volume two. And so if you have a graph, if you go from your initial volume to your final volume, your integral gives you the total area underneath the curve. But doing things differential wise actually helps us, uh, can help us figure out a number of different expressions. And so, of course, with our work, we're using P instead of P external. We're able to do that because we're holding pressure constant. So the pressure on the outside of the system versus the pressure inside the system are going to equal each other because pressure is constant. Okay, so let's look at how to break the enthalpy equation down into differentials. The differential change of our enthalpy, get the differential change of internal energy plus the differential change of P times V. Now, to figure this out, you're going to have to use something that calculus calls the chain rule, where, oh, let's just say you have the differential of x times y. This is going to, you have to take the differential of 1. So you have 1 times the differential of the second one plus the second one times the differential of the, so x times the differential of y plus y times the differential of x. This is called the chain rule for your derivatives. And so what that's going to give us, oh, so this is going to be PDV plus VDP. Now, if U is Q plus W, what we're going to get here, now don't pay too much attention to what I did there. Those are deltas. So Q and W, they're not state functions. So you have to do path integrals to figure them out. We're not going to do that. So just know that those are improper, like, is improper the word? Yeah, improper differentials. So they're not a complete differential. So, however, you can get a proper differential out of that by doing PDV. So your improper differential W becomes PDV. And so then you substitute that in. Okay, so you're going to get delta Q minus PDV plus PDV plus VDP. And you notice that these two subtract out. But remember, P is constant, and dP is a change. So your differential of pressure is a tiny change in your pressure, but if P is constant, that means any change in pressure equals zero. So you're going to get differential of your enthalpy. It's going to be your delta Q. Now, what we're going to do is we're going to integrate this system. Okay, so let's see. We're going to call that H prime now. No particular reason, it's just in calculus because I'm going to have limits here. Initial enthalpy, final enthalpy. And so calculus doesn't like you to have the same variable inside your differential or inside your integral that you have in your limits. So like if your limits are h and then you have h inside the equation in your integral, calculus doesn't like that. So I just put a little prime on it to say this is some kind of placeholder for enthalpy. And so from position 1 to position 2 of your delta Q, now what you get is so that's why we have this up here. So this definition, when you have the integral of a differential, your integrals are your antiderivatives. So that's just going to reverse the differential. So what you're going to get out of this differential is H prime. So the placeholder for enthalpy evaluated from initial enthalpy to final enthalpy equals QP. Again, that integral of the improper differential is just going to give you back Q. There's a whole lot we could get into about that. We just don't need to for this situation. And again, this here is the same thing as this here. Remember, I just put the prime on it because calculus doesn't like me to have an H here and an H here. So I put an H prime to say, okay, fine, they're not the same. I'm just putting a placeholder in the integral to make any calculus professor that might see the lecture happy. Most of the time in physics, we do things that leave calculus teachers going, you can't do that. And we always go, yeah, but it works. So now the way you do an evaluation from calculus is, again, my integral. My differential, reverses the differential and just gives me what's inside the differential, because the integral is the antiderivative. And so the way an evaluation works is my limits, it's a difference. So now this is going to be, you put your limits into your equation, final enthalpy minus initial enthalpy equals QP. So once again, we're getting delta H does equal the heat for a constant pressure system. However, there is another form of the enthalpy equation that you see more often, and you can use the differential procedure to get there. Okay, so once again, we're going to have our dH equals du plus P dV plus V dP. P is constant. And if P is constant, that means any change in P is zero. So that whole term becomes zero. All right, now I'm going to end up integrating this whole thing. And since I have H in my limits, to make calculus happy, I'm just going to put a prime on my differential to represent a placeholder, waiting for the solution to the integral. Another way to think about it, like let's say you're integrating x squared dx, and then your limits are actually x1 and x2. Well, calculus doesn't like for you to have x's in the limits and in the equation that you're integrating. So then you go, oh, well, x prime, x prime. Well, that it's just to set apart, like, yeah, I know. I'm waiting for the solution to the integral and evaluation at the limits. Okay, so then we're going to get an integration on this side. Let's see, from an initial value to a final value, du prime plus p dv prime. The way integrals work is now compute, and this is going to be initial energy, final energy for du plus initial volume, final volume for PDV. You're always going to have some kind of equation and then a differential that matches one of the variables in your equation. That variable is the one you're integrating over. Now, the way integrals work is P is constant, so constants can pull outside of the integral just the same as they can with sums. Like let's say I had the sum of P times V, and I'm summing over V. Well, P is a constant, so it can pull out in front of the sum. Same thing here. So now I'm going to get So the constant just pulls out of the integral. And now I can solve everything. They're all integrals of differentials, which means I'm just going to get back what's inside the differential. So here, you're going to get h prime evaluated at the limits, u prime evaluated at the limits, plus p b prime evaluated at its limits. Okay, and so I'm going to get, I don't need to put it down that side, h final minus h initial is going to equal u final minus u initial plus p v final minus v initial, which if you're looking at this, what this becomes is our more notable version of our enthalpy equation. It's going to be delta H equals delta U plus P delta V. So this is the one you'll see more often. So I'd make sure you know this equation and get used to using it as we're going along. So let's start with an exercise that's just based off thermodynamic logic. So here we have a reaction 25 Celsius, 1 atmosphere. Fluorine gas is becoming so fluorine gas is becoming a gas of fluorine atoms. And so fluorine gas, of course, is F2. It's a diatomic molecule. The atoms are just single fluorine atoms. So we have 1 mole of fluorine gas becomes 2 moles of fluorine atoms. What are the signs of Q and W? So positive, negative. So the first thing you want to notice is that every fluorine atom, every fluorine molecule, so there's a bond there, becomes 2 fluorine atoms. So what happens is a bond is broken. The bond between the fluorine atoms has to be broken in order for this to occur. So because a bond is broken, Q is positive because heat energy has to be put into the system to break bonds. You cannot break bonds without adding energy to the system. Well, what about W? So in the beginning, we have 1 mole of gas. After the reaction, we have 2 moles of gas in the chamber. So we have more gas in the chamber, but the pressure stays 1 atmosphere. So the pressure is constant. So the only way that's possible is for an expansion to occur. So the volume has to get larger. More gas for pressure to stay constant, volume has to be larger. So if we think of work, negative P external delta V, we know that delta V is positive because the system is getting bigger. Work is going to be negative P. Well, you can call this the 1 atmosphere. And then whatever delta V is. And so that means that W has to be negative because for an expansion to occur, the system has to do work on the environment. So work leaves the system. So work is going to be negative. Okay. What about this? Let's consider this reaction. It's the combustion of methane to form carbon dioxide and water. The enthalpy of this reaction is a negative 891 kilojoules. calculate the enthalpy change for each of these following cases. It might seem like we already have that answer, but we don't really. Okay, so 1 gram of methane is burned in excess oxygen. So that just means that methane will run out. So we don't have to, that tells us we don't have to do a limiting reactant calculation. All the methane will be burned. Okay, so for A, what is the delta H for this? Well, what do I know? The mass of my methane is 1 gram. CH4 itself is 16.04 grams per mole. All right, well, let's figure out what the delta H for this is, because I want to show you how to use the delta H for a reaction. Let's see, so we have 1 gram of methane. Let's see, and then that is 16.04 grams per mole. You want to get this into moles because now you're using the coefficients from the equation. And of course, you know that technically in front of the methane, there's a 1. So that means for every, and here's how you use it. For, this is CH4, whoops. For every 1 mole CH4, so there's my coefficient, I get negative 891 kilojoules of energy. Okay, so then I multiply all this up, and for the 1 gram of methane, I get negative 55.5 kilojoules. So when you're seeing chemical equations with an enthalpy attached to them, that's for the moles, the coefficients, the stoichiometric coefficients you see in the chemical equation, and the moles those represent. So part B, 1.0 times 10 to the third liters of methane gas at 740 torr and 25 Celsius burned in excess oxygen. So again, we're not worried about limiting reactant. What is the enthalpy? Okay, so pressure. Let's see, 740 torr, temperature, 25 degrees C, volume, 10 to the third liters, and then R, because it's a gas calculation, 0.08206 liter atmospheres, moles, kelvins. All right. So again, to be able to do this, we need moles. We need moles of CH4 because again, this number here is going to relate to 1 mole of CH4. Okay, so EV equals nRT, or the moles that we need, EV over RT. But we see that our pressure and our temperature don't match the units in R, so we have to fix that. $740 torr. We remember that 1 atmosphere is 760 torr. This is going to give us a pressure of 0.974 atmospheres. Temperature, 25 Celsius plus 273. That is going to be 298 Kelvin. And now we can calculate moles. Okay, so R, 0.08206 liter atmospheres over moles kelvins. Temperature is 298 K. Pressure, 974 atmospheres. And then volume, 1.00 times 10 to the third liters. We are going to get, let's do it, put it down here. That is going to give us 39.8 moles of CH4. And now we can say, well, 39.8 moles of CH4 and for every mole of CH4, I have a negative 891 kilojoules. That means that my enthalpy for this reaction is a negative 3.55 times 10 to the fourth kilojoules. And I hope you remember that all of these reactions have a negative delta H, which means this is an exothermic reaction. You're always going to want to make sure you can bring stuff like that up quick in your head. All right, moving on to calorimetry. Okay, so calorimetry is a pretty important laboratory procedure. So basically what you have is your calorimeter. Usually what we do in lab is called the coffee cup calorimeter. It's open to the environment, but your calorimeter has a fluid in it, usually like water, some kind of coolant. And then, so like for the bottom calorimeter, you will have a chamber where a chemical reaction occurs, and then uh, heat is going to evolve from that system. And then you're going to measure the heat change. Once everything equilibrates, you're going to measure the change in temperature and do your calculations from there. For example, usually in our first year lab, what you'll do is you're going to, for example, like mix a strong acid and base in your calorimeter. So you'll have water in your cup. You want to make sure you have multiple styrofoam cups stacked so that you get insulation for the environment inside. And then when you mix and you just put the acid and water straight in, but you'll notice that the whole system gets warmer. And so what happened is those two chemicals interact. It's an exothermic reaction, the neutralization. So they put heat out, which makes the entire solution warmer. So it's the same idea, except your chemicals are just in the solution and they're putting heat out into the water that you put them into, so it warms up the solution. It's still exothermic. You can work with physical changes, chemical changes. Uh, the big thing to think about is the total Q of your system. The total Q is going to equal zero because your system is either going to expel heat or bring heat in, and it will either expel heat into the surroundings or pull heat in from the surroundings. And so the Q of your system plus the Q of your surroundings is going to equal zero. So the Q of your system is going to be the opposite, a negative Q of your surroundings. This is one of the keys to calorimetry. You also are going to have your path equation that's going to be really important. Your new equation for Q, which is right here. You can see this done in different ways. I put in the Q equals MC delta T. So M is mass, C is going to be your specific heat capacity, delta T is change in temperature. You can see heat capacities in different ways. So your specific heat capacity, I use a C sub S. And that's going to give you units of joules per degree Celsius times grams or joules per Kelvin times grams. The textbook that you're reading, instead of using a C, uses an S. You could also have molar heat capacities, joules per degree Celsius times mole, joules per Kelvin times mole, or total heat capacities, joules per Celsius or joules per Kelvin. It's really just going to depend on which heat capacity you have. So in the path equation I put on here, I included mass in the calculation because your specific heat capacity has grams in its units. So I need to multiply by mass to cancel out those grams because at the end, Q is going to be in units of joules. And then your heat capacity is always going to be heat absorbed over the increase in temperature. So a lot of books, you'll see how much heat is needed to raise the temperature by 1 degree Celsius. Well, so it's like how much heat do you need per degree Celsius? That's a heat capacity. And each material has its own heat capacity. So here we have what's called constant pressure calorimetry. So this would be like your coffee cup calorimetry. And so it's open to the environment, so the pressure is going to stay the same because, well, it's open to the atmosphere. Okay, well, as we know, in constant pressure, delta H is going to equal your Q. Now, you're going to want to pay attention because it is going to equal your Q. You're going to calculate Q. You'll usually get joules or kilojoules for Q, but then you're going to want to make sure you are taking your delta H to kilojoules per mole. It's just a little bit of an adjustment. Usually, so when I give you an exercise to do, I'll tell you what units to end in, and then you're just going to take what you have and make sure you end up there. Um, I'm using that subscript to mean reaction. So up here, your system would be your reaction. So the whole part of calorimetry is we're trying to measure and calculate energy exchange based off change in temperature. And so a more straightforward version of the heat equation from above is right here, Q equals MC delta T. And so you notice I put C sub S, which is your specific heat capacity. And that's why I have to include multiplying by mass. Your textbook, as I said, gives you MS delta T. I don't really care which one you use. I always used MC delta T, but if you're more comfortable using S, then go for it. So the way you can think about it, you're going to get a heat transfer. You're waiting for equilibrium. So here is an example of a hot metal being put in water. That hot metal starts expelling heat into the water. So your system is exothermic. It's putting the metal, your system, it's putting heat out. The water's collecting that heat, and eventually, over here, the water and the metal are both going to have the same temperature. That's where you're going to do your measurement, and you're going to know what the temperature of the water was before, what's the temperature after everything equilibrates, and you're going to figure out the heat energy that was exchanged. So it can go the other way. The reaction can make the water make the whole make the water around it colder. So it was in so say it was endothermic. Well, then it's going to take heat in, and your temperature is going to go down when you test at the equilibrium point. So see, the heat of reaction is an extensive property. So extensive properties depend directly on the amount of substance. So for example, you double your reactants, you double your heat produced. Intensive properties are properties that don't depend on amount of substance. So we have one definition, we'll put it the opposite. So for example, the density of a material is an intensive property. Like if you have a chunk of not carbon, copper, the density of copper is the density of copper. I could have more or less. I could have a bigger chunk, a smaller chunk. It's same density. Okay, so here, in a coffee cup calorimeter, which is our constant pressure open to the environment, 100 milliliters of 1.0 molar sodium hydroxide and 100 milliliters of 1.0 molar hydrochloric acid are mixed. Both solutions were originally at 24.6 degrees Celsius. After the reaction, the final temperature is 31.3 degrees Celsius. And now, again, usually in your coffee cup, we would mix these in, there would already be water in there. Assuming that all the solutions have a density of 1 gram per cubic centimeter and a specific heat capacity of 4.18 joules per degree Celsius times grams, calculate the enthalpy change for the neutralization of the hydrochloric acid. Assume that no heat is lost to the surroundings or to the calorimeter. Okay, so what we're being asked for, delta H. Things that we know. Concentration of sodium hydroxide equals our concentration of hydrochloric acid equals 1.0 molar. Okay, so the volume of each one is going to equal each other. That's our 100 milliliters. Let's see, T1 is 24.6 degrees Celsius. T2 is 31.3 degrees Celsius. And so again, the way you think of this, let's say you have your system is the chemical reaction. Your environment is the fluid in the calorimeter. When the molecules react, when the hydrochloric acid and sodium hydroxide molecules react and neutralize each other, that's your system. That neutralization is going to be exothermic and it's going to release heat. And so all of the fluid in there is going to get warmer. So that's heat being put into the surroundings. Okay, so the density, but we know this is also 1.0 grams per milliliter. And our specific heat capacity, 4.18 joules degrees Celsius times grams. Okay, so let's see. So since we were able to measure the temperature change of the environment, the Q we're calculating is for the solution. MC delta T. Okay, so the mass that we need, 200 milliliters of solution. How did I get that? I have 100 of that, 100 of that. And it's the density of 1 gram per milliliter. This is going to give me 200 grams of my solution. Now, most of our calculations we've done, we've switched from Celsius to Kelvin. You have a situation here where your constants are in terms of Celsius. So don't change your temperatures. Remember, match your constants. Um, if in doubt and you don't have a constant in Celsius, change to Kelvin. But here you have a constant in degrees Celsius, so leave things that way. Okay, so the Q, we're going to see what the heat for the solution was. So for your environment, 200 grams, 4.18 joules degrees Celsius times grams. And then our final temperature is 31 degrees, 0.3 degrees C minus 24.6 degrees C. This is going to give us a Q of 5.6 times 10 to the third joules, or 5.6 kilojoules. So Q is positive. And this is the Q, this is the heat energy that was gained by the entire solution. Okay, so that means that the fluids in the chemicals inside of this calorimeter got warmer. So if the entire environment, if the entire thing got warmer, that means heat was evolved from the reaction between the sodium hydroxide and the hydrochloric acid. Okay, so if heat was evolved from the reaction into the environment, making the solution warmer, that means it was an exothermic reaction. Let's remind ourselves of what this reaction is. Okay, so we have the chemical reaction equation. Where'd the rest of that go? Okay. So then the question is, how many moles of HCl were neutralized? We're going to need that because remember, we want an answer in kilojoules per mole. Our delta H is going to be in kilojoules per mole. Okay, so 0.10 liters HCl, a mole per liter is going to equal 0.10 moles of HCl. Now, because of the stoichiometry of this chemical equation, we also used 0.1 moles of sodium hydroxide to neutralize. That I'll explain why that's important in a minute, because it has to do with when you find your enthalpy and you have kilojoules per mole. Well, moles of what? Which one, the sodium hydroxide or the hydrochloric acid? Well, in this case, they're equal, so it doesn't really matter. Okay, so of course we remember that the Q of our system equals the negative Q of our surroundings. We were only able to measure the surroundings. And so this is what means that the heat energy of our system is a negative 5.6 kilojoules of energy expended. So remember, the system is the individual molecules of sodium hydroxide and hydrochloric acid reacting. When they react, they release heat. That was the change in that heat then led to the change in temperature that you measured in the entire environment, the surroundings. Okay, so our delta H is going to be the Q of our system over our moles of HCl, or negative 5.6 kilojoules over 0.10 moles, and our delta H is going to be negative 56 kilojoules per mole. Now, I said this time it didn't matter. We could just put the 0.1 moles, we divide by the 0.1 moles because they're both equal. If you run into a situation where your reactants are not equal, you'll end up dividing by the limiting reactant, the moles of your limiting reactant. So that's why it matters. This time we had equal amounts, so we didn't have to worry about it. But just in case you have different amounts, find out which one is limiting, and that's the number of moles you divide by, because that's the maximum amount of enthalpy that can be evolved from the reaction. Okay, so constant volume. We have some new equations for delta H. So here's one equation. So delta H is uh, the change in the internal energy of the system plus the change in the moles of your gas times RT. Okay, so the change in moles of your gas is moles of your gaseous products minus the moles of your gaseous reactants. That's because here our constant volume, a good example of this is the bomb calorimeter. Here you can see the water in the surroundings. You can see the reaction chamber with O2 that's pumped in there. And then you have your little tips there that'll spark the reaction. Uh, and so maybe you have a reaction where no gas is produced, then you would use O2 gas. You get fewer moles of O2 gas and no moles of gas produced. So that would give you a negative delta N. So you just, or let's say you had 2 moles of O2 used and you produce 5 moles of gas. Well, that'd be 5 minus 2 or 3 for your delta N. It's just your moles of gas products minus moles of gas reactants. And you're like here in this case, your gas reactant is O2. And so then that reaction is going to happen, and then heat energy is going to flow through the chamber there into the water, and then you're going to measure the temperature change of the water. So the reason that delta H is a little different this time is let's think about what happens. These are uh, constant volume situations. So let's start with our delta U equals heat plus work, which we remember. So constant volume, QV, Q sub V minus P delta V, constant volume, delta V is 0. So what we get is delta U equals RQ sub V. So in this case, the heat that we're talking for constant volume systems, heat is going to be a measure of the internal energy of the system. And so, for a system at constant volume, we could make an adjustment. So let's start with our enthalpy equation, delta H, delta U plus P delta V, which technically is going to be delta U plus delta PV, or delta U plus delta nRT, or delta U plus delta N RT. So again, you're looking at that change in moles. R and T are constant. And in this case, we treat temperature as constant because we're really looking at the temperature we measure at equilibration. Like for example, what you see in this image, you see a combustion. You know that temperature is going to spike up real fast. You know it's not necessarily constant. And then as the water and the chamber equilibrate, temperature is going to change. So it's like, well, how can you treat temperature as constant? Because what you're measuring is that final temperature, that equilibrium temperature, and then you're looking in that change in moles of your gas of whatever products you produce, versus subtract, and then you subtract off the gas of the moles of your reactants. So of course here you have QV plus delta nRT. So there's one form of enthalpy for a constant volume system. Let's see, here is another form of enthalpy for a constant volume system. So you see your QV equals MC delta V times V delta P. Okay, well, we can get to that through our differential format again. So we start with H equals U plus PV. We have DH. As you remember, this becomes DU plus PdV plus V dP. and it's constant volume. So the V is 0. So any change in volume is 0. So we're going to get U, an infinitesimal change in internal energy, plus VDP. Now, by our definition that we start with, our heat capacity is going to be the change in energy, change in temperature. So this is the temperature derivative of internal energy, or du is going to be CV dt. And so then that means that our dH can become CV dt plus VDP, and then we're going to integrate everything. Your C there, your heat capacity is a constant. So let's see. So that means that it comes out in front of the integral. T initial to T final. dt, your volume is a constant, so it comes out in front of your integral. Yep, rhymes. Nope, not T. Initial pressure, final pressure, P. Okay, so when we solve those, we just the integral of a differential, we are going to get what's inside our differential back, evaluated at the limits. And so our evaluation is a difference. So we have final minus initial, CV, T final minus T initial, plus V final minus initial. So we're going to get our delta H equals our heat capacity, delta T plus volume, delta P. We could leave it this way. This heat capacity here is in terms of joules uh, degree Celsius. And so that'd be our total heat capacity. But most of the time we're working with a heat capacity that's per degree Celsius times grams, or per degree Celsius times mole. So we're going to end up changing that to our M. Put that mass in there so that we can get everything in terms of joules or kilojoules. And so once again, we're back at QV plus V delta P. So the way you leave that equation is really going to depend on the heat capacity you're using. This one has joules per degree Celsius times grams. If I take out the M, then it's just in joules per degree Celsius. So again, it's just going to depend on which heat capacity you're using. Okay, so let's see, we have the combustion of 0.1584 grams of benzoic acid It increases the temperature of a bomb calorimeter by 2.54 degrees Celsius. So remember, you're measuring the water in the surroundings. And so that's the temperature change you're getting. Calculate the total heat capacity in kilojoules per degree Celsius of this calorimeter. Let's see, the energy released by combustion of benzoic acid is 26.42 kilojoules per gram. Let's see, a 0.2130 gram sample of vanillin is then burned in the same calorimeter, and the temperature increases by 3.25 degrees Celsius in the surroundings. What is the energy of combustion per gram of vanillin and then per mole of vanillin? Okay, we're being asked for the heat capacity of the calorimeter. Our energy of combustion in kilojoule per gram, energy of combustion, kilojoules per mole. All right, so my mass of benzoic acid, 1,584 grams. The first change in temperature is 2.54 degrees Celsius. Change in energy of the benzoic acid, the energy released by combustion. So it's a combustion, and releasing energy, of course, is going to be a negative value. Okay, so then the mass of your vanillin, 0.2130 grams. The delta T of that reaction, 3.25 degrees Celsius. And then I'm going to end up needing the molar mass of vanillin. If you're making your own list, you might not know this at the start. So if it's not in your list, don't worry about it. Again, yours don't have to match mine. You just need to make yourself a list of known values that can help you solve the problem. Okay. And once again, remember your textbook, I use delta U. That's the more traditional way to write it. Your textbook is going to use delta E. And so the textbook's delta E equals my delta U. So same thing. Okay, so the heat capacity of the calorimeter. Well, we remember that heat of the calorimeter plus the heat of the reaction is zero, which means the heat of our reaction must be the negative heat of the calorimeter. Okay. And so then we're going to say, well, delta U is Q plus W, or Q minus P delta V, but it's constant volume, so that's zero. Delta V is zero. So that means our delta U equals our heat. Okay, well, let's try and figure this. So the heat of our reaction is going to be the mass of our benzoic acid times the delta U of our benzoic acid. And so that's going to be 0.1584 grams. There's a negative 26.42 kilojoules per gram. And again, if you weren't sure what to do, just think and say, well, heat Q has to be in terms of joules or kilojoules. I have grams and I have kilojoules per gram. Well, I'm going to have to multiply those two to get rid of grams and get kilojoules. So that look at the units you have and look at the units you need. That can help you set up your problem or your solution. So this is going to be negative 4.185 kilojoules of heat. So in the beginning, if you didn't realize that this delta U is negative because it's heat being evolved from the benzoic acid, once you get down here and you got a positive number, ask yourself, okay, this reaction is a combustion. A positive Q from the standpoint of the reaction means energy was taken in. It was an endothermic reaction. Is a combustion an endothermic reaction? Well, no, it's not. So I have the wrong sign. I need to make sure it's a negative. Okay, well, then the Q of the calorimeter will be negative Q of the reaction. And so that means that the calorimeter is going to get, so the water in the calorimeter is going to get warmer. So it takes in a positive 4.185 kilojoules of heat energy. And then, of course, we say that the Q of our calorimeter is going to be the heat capacity, the total heat capacity of our calorimeter times the change in temperature, or the total heat capacity of our calorimeter is going to be our heat energy divided by delta T. And so in this case, that is going to be 4.185 kilojoules divided by 2.54 degrees Celsius. So our first answer is going to be 1.65 kilojoules per degree Celsius. Okay, so now we have the heat capacity of our calorimeter. Okay, so what are our various internal energies? Okay, we need to know, now we need to know the new heat energy of our calorimeter that put into our calorimeter. There's our heat capacity, delta T. So the heat capacity we just found times the 3.25 degrees Celsius from the vanillin combustion. That means the heat energy given to the calorimeter is 5.36 kilojoules. Okay, so well, we know that our delta U of our reaction is going to be, so if we're working towards kilojoules per gram, the Q of our reaction divided by the mass of the vanillin, or the negative Q of the calorimeter divided by the mass of the vanillin. Okay, so this is going to be a negative 5.36 kilojoules divided by the 0.2130 grams of our vanillin. And so our first delta U, so what exactly did it say? What is the energy of combustion? So our first energy of combustion, so the energy of our reaction, is going to be a negative 25.2 kilojoules. That's awful. Kilojoules per gram of our compound. Okay, what about delta U in kilojoules per mole? Okay, well, we can do this in an easy way. So delta U, I'm going to take my negative 25.2 kilojoules per gram. And I know that vanillin is 152.15 grams per mole. That means that the energy per mole of our combustion is a negative 3834 kilojoules per mole. These calculations really aren't bad once you get used to your signs. You're going to have to really practice on what is the system, what is the environment. Remember, in thermodynamics, the universe is system plus environment. So make sure as you're going through this stuff, you're practicing what sign is which, what are you being asked for? Because that's going to be key to solving a lot of problems in thermodynamics. All right, so we'll finish this on Thursday. I'm not here tomorrow because the campus is doing, I don't know, electrical shutdowns to work on stuff, so I can't be here without electricity. But we will finish this on Thursday and get into chapter 7, and we're just going to keep plowing ahead. All right, talk to you later.